Good morning, everyone, and thank you for joining. Welcome to today's webinar, where I will be discussing OMRON's B5L Time-of-Flight Sensor Module, providing 3D vision for autonomous mobile robot applications. My name is Kyle Alberti. I'm an Application Development Manager with OMRON Electronic Components, responsible for product promotion to the AMR industry. Jason Montgomery with EE Tech will be on after the presentation to help lead us through the Q&A session. So before we begin today, I would like to bring up a poll question for the audience to really understand what brings you to today's webinar. Are you joining today for general interest? Are you interested in replacing your current 3D sensor with a time-of-flight sensor? Or are you looking at it for a future project that could utilize 3D vision technology? We'll give about 10 more seconds just to get a few more answers in. Great. So what is a time-of-flight sensor? There are many different kinds of distance sensors, each using different technologies to provide distance information for 3D vision. Time-of-flight is a distance measuring method that calculates distances using the time it takes the emitted light waves to be received back. Time-of-flight sensors use optical sensing technology in combination with active light. There are two types of time-of-flight sensors, direct and indirect. Direct time-of-flight measures the undeviating time it takes the light to go from the emitter back to the receiver. It can kind of be thought of as using a stopwatch type of approach where the sensor sends out a short pulse of light and measures the time until the echo hits the sensor. Direct time-of-flight sensors are best for using only a single or maybe a couple of points, sort of like a rangefinder. Indirect time-of-flight measures the phase shift between the emitted and the received light, where the phase shift is proportional to the distance. Indirect time-of-flight is best used for 3D imaging. Using the indirect method, OMRON's B5L Time-of-Flight Sensor Module calculates distance based on the phase shift between the emitted and received light. The extensive distance data is then converted into 3D point cloud data. The infrared light waves are emitted in short pulses and reflected back to the dedicated image sensor, and then fed to OMRON's distance calculation circuit and converted to output the distance image. The distance signal, or depth information, is the output from each pixel. The ToF Sensor's pixel array uses customized CMOS sensors, allowing the module to have high speed and high sensitivity. On OMRON's demo software, short distances are displayed in red and yellow, while longer distances are displayed in blue and green. You can see from the example here how the 3D image is created from the distance signal of each pixel, converted into point cloud data to achieve real-time 3D vision. The calibrated output signal provides the X, Y, and Z coordinates for easy design integration. The distance outputs can be changed into several formats, including the orthogonal coordinate form, orthogonal coordinate rotation form, polar coordinate form, and amplitude data only. It's time for another poll question. I would like to know what type of 3D vision sensor you are currently using in your application. Are you using ultrasonic, stereo, structured light, time-of-flight, or another type of 3D sensor? Or are you not currently using any 3D sensors in your application? I'll give about 30 seconds. Very good. Now I'd like to discuss some of the features of OMRON's B5L Time-of-Flight Sensor module. The B5L sensor has many features and advantages compared to other 3D vision sensors on the market, including high light immunity up to 100,000 lux, high precision at plus or minus 2% at 2 meters, a long life equivalent to 5 years under continuous use, and interference prevention function for up to 17 units simultaneously. I will go into a little bit more of each of these features in the coming slides, but for some additional specification details, the B5L is QVGA with 320 by 240 pixels. It is rated to measure distances from 0.5 meter to 4 meters and features a 90-degree horizontal by 70-degree vertical field of view. So as I mentioned, the B5L features high ambient light immunity up to 100,000 lux. The high performance is achieved by OMRON's lens filter design corresponding to the emitted LED wavelengths, proper arrangement of the emitters and receivers, and OMRON's optical simulation technology. You can see from the test data on the left that the B5L has a high measurement accuracy and stability ranging from 0 to 100,000 lux. On the right, you can see test images showing the B5L's ability to detect objects even when facing direct sunlight. So whether the B5L is in direct sunlight or just normal daylight conditions, the sensor can reliably detect the objects within its field of view. Continuing on with the light immunity of the B5L, here you can see from an indoor environment that the measurement results are not affected by ambient light conditions either. On the left, we display the environment without ambient light, and on the right, we display the environment with ambient light. Again, you can see the measurement results remain stable and reliable and are not affected by the ambient light conditions within this environment. The B5L achieves a high output accuracy by outputting compensated signals to minimize control processing on the end user's actual machine. As I mentioned, the sensor is rated at plus or minus 2% at 2 meters. From the test data here, you can see that the sensor features stable accuracy that varies linearly with the distance. The B5L also features high accuracy in the angular directions thanks to OMRON's internal software technology for calculation processing, compensation processing, 3D conversion processing, and image filtering. The B5L sensor features high reliability with its long life design, giving consideration to high work efficiency. The sensor is able to achieve a long life of up to 5 years under continuous use thanks to OMRON's unique circuit design and heat emission design with aluminum casting and heat sink. In the next slide, I will show a video demonstrating the complete external design of the sensor. The B5L features a built-in interference prevention function, allowing for up to 17 units under simultaneous operation. By changing the sensor's ID, the user can change the emitted LED frequency, ranging from 11.6 MHz to 12.4 MHz, preventing frequency interferences between the multiple units. In the next slide, I will show a video featuring 2 sensors, each using a different ID. With these sensors set at different IDs or frequencies, you can see that they are able to provide a stable and reliable detection and avoid interference from one another. The B5L features a built-in high dynamic range function, or HDR function, that controls the shutter speed and performs the measurement multiple times, combining both short and long exposures to provide a comprehensive view of the environment. Whether operating the sensor in open or closed environments, the sensor's HDR function is able to ensure an accurate measurement of near and far objects, regardless of color, reflectivity, ambient light, and many other conditions. With the ENR function enabled, the sensor is able to simultaneously detect short and long-range objects, even with a high range of reflectivity. Disabling the HDR function enables the sensor's high-speed operation mode, calculating distances from only a single measurement. The last feature I would like to highlight is the built-in edge noise reduction function, or ENR function, that is capable of determining the edges of an object and reducing the noise associated with these edges. Data can be removed when there is a large difference in the distance between pixels. Pixels whose distance difference is greater than or equal to that ENR threshold value are determined as boundaries, or edges. This function will output the distance and amplitude value of the farther pixel as a hidden amplitude. Reducing edge noise allows the sensor to reliably detect objects by enhancing the object's outline in order to minimize the likelihood of noise or false detections associated with this noise. At this time, I'd like to bring up another poll question. I would like to know which feature of the B5L is most important for your application. Is it high ambient light immunity, high precision, long life, interference prevention, measurement distance range, or a wide field of view? And I'll give about 30 seconds. Okay. I would now like to move on to applications of the B5L for 3D vision sensing. The B5L provides 3D sensing for object detection and environment recognition. The use of extensive distance information enables the sensor to identify its peripheral environment with a 90-degree horizontal by 70-degree vertical field of view. 3D vision sensors are seeing interest in many diverse applications, including logistics and conveyance, patient monitoring and observation, and automatic detection for people counting and traffic flows. But our current focus for today is on the AMR application for environmental recognition and obstacle avoidance. Autonomous mobile robots are increasingly being used to move goods and materials for sorting, order fulfillment, and many other use cases. These robots require sensors to provide 3D vision to accurately view the surrounding area and to safely and efficiently navigate in challenging environments. The B5L sensor offers real-time 3D vision even in the most difficult conditions. For AMR applications, the B5L is providing an alternate and cost-effective solution to LiDAR. 2D LiDAR is expensive and requires several sensors to cover a wide field of view. 3D LiDAR is available to detect that wider field of view, but of course comes at a much higher price tag. The B5L provides a wide-angle detection area for many AMR applications, including obstacle, step, and overhang or cantilever detection. The B5L is solving many perception problems, not only with LiDAR, but also many other 3D vision sensor technologies that are currently available on the market, including ultrasonic, stereo, structured light, and others. The video on the next slide shows the B5L being used in a warehouse AMR application, demonstrating the B5L's real-time 3D vision capabilities. The next video I would like to show shows the B5L on an AMR in a narrow corridor environment. I would like to highlight that this environment has a significant increase in surrounding object reflectivity from the previous warehouse environment. But this does not affect the ability to accurately detect obstacles or the environment. Lastly, I would like to show some results from common AMR application tests we have done. On the left, you can see the B5L's ability to detect black and shiny objects within the sensor's field of view. On the right, you can see the sensors testing for forklift time and pallet detection. The sensor can reliably detect these objects by refining the B5L parameter settings to fit your environment and application. Software and sample codes. We currently have several software and sample codes available for the customer to evaluate the sensor. Here we have a Windows-based SDK evaluation application available, allowing customers to evaluate the sensor from their computer or laptop for a quick evaluation. The user can quickly and easily change parameter settings and output data from the user-friendly interface in order to fine-tune the sensor for their application environment. For a more comprehensive evaluation, we also have several additional sample codes available for the B5L depending on the preferred language. Currently, we have sample codes available for ROS2, Python, C#, and C++. There's one last demo available that I would like to highlight. OMRON has been developing a skeleton detection algorithm paired with the B5L sensor to reliably detect human presence and movement. We are looking to integrate this into the sensor as early as next year, but currently have available as a supplemental sample code. In the next slide, you can see video of this demo in action, showing the real-time movement and tracking of a person using the B5L sensor. Okay, thank you all for your responses to the poll questions today. Well, this concludes my presentation for today. I'd like to thank you all very much for attending and your input on the poll questions. Again, my name is Kyle Alberti, Application Development Manager for AMR Industry. I have my email on the screen at kyle.alberti@omron.com. Please feel free to get in touch with me for more information, any questions you may have, or how the sensor may be a good fit for your specific application. To learn more about the B5L, other OMRON sensing products, or our component lineup, including relays, switches, and connectors, I encourage everyone to visit our website at components.omron.com. I would also like to mention that OMRON will be hosting our next webinar with EE Tech for patient monitoring with Carrie Horan, OMRON's Sensor Products Manager, on October 7th. Stay tuned for more details on this webinar coming soon. So again, thank you all very much for your time and joining with me today. Jason, I'll pass this back to you and we can get to the Q&A session.
Thank you, Kyle, for that excellent presentation, everyone. This is Jason Montgomery with EE Tech and All About Circuits. Kyle, let's just dive into some questions here. I know we've got a lot of things going on here. So first question that I'm seeing is, how well can the sensor detect dark or black objects?
Sure, good question. So the B5L can detect absorptive color with an increase in the integration time. So by increasing that integration time, it really allows for absorptive colors to be detected. But as a trade-off, we have highly reflective objects in the environment that may become saturated. So you'll really want to fine-tune these settings based on the environment and use case.
Got it. Thank you very much. Next question that I'm seeing, Kyle. What are the scenarios where the sensor might have difficulty detecting things?
Yeah, another good question. So I would say for that, it's very dependent on the environment and the parameter settings being used. So as I said, it can offer difficulty for highly reflective or transparent objects such as mirrors or glass or objects like that, and also for low reflective objects such as the black objects in the previous question. And then additionally, I would say objects that are set at a distance of over 12 meters can also be difficult and out of view of the sensor. So with that, you will really want to fine-tune the parameter settings based on the application and the environment of the specific application to maximize the sensing capabilities, and again, based on the objects that are in that environment.
And what could cause false positives, inaccurate measurements?
Okay. Most false positives can happen when there is a low signal, either from objects that are too far or too dark, or it can happen from saturation with objects that are too reflective or too close in that environment.
Okay. What's the trade-off relationship between integration time and detection distance?
So with that, I would say, so if you shorten the integration time, shorter range or more closely ranged objects with higher reflectance become detectable, but longer range objects become a little bit more difficult to detect. And the opposite is true if you lengthen that integration time. Then the long range objects with low reflectance become easier to detect, while shorter range objects may become saturated and more difficult to detect.
I think this next question might tie into that. Can it detect objects within half a meter?
Yeah, so we have the sensor rated at the accuracy of plus or minus 2% at 2 meters. The sensor is capable of detecting within the half-meter mark by decreasing the exposure time, but with that, the accuracy won't increase from that 2%. So as the sensor really just doesn't have an accuracy correction for those closer targets.
Got it. Thank you very much. Let's see some more questions here, Kyle. Is the sensor safety rated?
No, at this time the sensor does not have a safety rating. That may be looked at in future iterations of the sensor, but at this time we do not.
And what's the power consumption here?
Good question. So I would say that the average power consumption for the sensor is around 0.3 to 0.4 amps, 15 watts or less. I think at peak with the highest integration setting, it can reach up to 2 amps, but again, average will be around the 15 watts.
Got it. Thank you very much. I have a question here asking if you can talk about the communication interface.
Sure. So currently the sensor is USB 2.0 Type B micro connection.
Got it. Is there overheat protection here?
Yes, very good question. So yes, the sensor does have temperature detection on both the image sensor board and the LED board. On the sensor board, power is restarted when the temperature exceeds, I believe it's 105 degrees Celsius. And then there is temperature detection on the LED board as well. So it will detect and turn off at 90 degrees Celsius, and then we have a redundancy on that to restop at, again, the 105 degrees Celsius mark.
Understood. Is there a warm-up time for the sensor?
Yeah, there is a warm-up time for the sensor. It takes about 20 to 30 minutes to stabilize before having that stabilization. So during that time, the sensor has a very slight increase in the distance. I'd say it's approximately 0.5% at the turn on, and then quickly stabilizes and again stable at that 20 to 30 mark.
Got it. Let's talk about the light source. Is that light source bad for your eyes? Do you need to avoid looking at it in certain ways?
Very good question. No, the B5L uses LEDs instead of lasers, so there is no risk to the users or the environment for that point.
What are the dimensions of the B5L?
The dimensions are 100 millimeters by 60 millimeters by 43 millimeters.
Perfect. Is it possible to change the number of pixels?
So at this time, it's not possible to change the pixel quantity there or count there. We are considering to provide VGA, so 640 by 480 in our next version of the sensor, but at this time it is remain at the 320 by 480. Excuse me, 320 by 240.
We got another question here. I'm going to try to make sure I'm getting this question right here. Do you have libraries available that connect the sensor to, I believe what they're asking here is a microcontroller?
That's a really good question. I don't know if I have the answer. I think that's something I would like to double check with our engineering development team. So that's something I can hopefully get back to you after the call on.
Great. And the person who submitted that question will be able to connect you all up, make sure you get the answers to that question.
Great. Thank you here.
Yeah. And everyone, these are great questions that are rolling in here. And if you have any other questions that have come to mind with this presentation, please let us know. We got a little bit of time here for some more questions as well. Kyle, in the meantime here, I'm going to try to rephrase this question here. I think the question is the OMRON 3D Time-of-Flight home design, is that an in-house design? Are you partnering with people to make that? I know they listed another company here. I don't know who. I think they're wondering who else is involved here, or if it's totally in-house with y'all.
Sure. Yeah. Great question. This is a OMRON design and product, so it is not partnered with any other company.
Understood. Kyle, is there anything else that you want to make sure we're touching on here, or anything else that we should recover? Any points you want to emphasize?
I'd just like to say that if there are questions that are coming in and it didn't somehow get answered. Again, please feel free to reach out to me at any time. I'd be more than happy to help assist in the questions or how the sensor could fit for your application. My email again is kyle.alberti@omron.com.
Fantastic. Well, Kyle, does that look like a good stopping point for us here? I think we got through the questions and the presentation. We good to wrap it up here today?
Yeah, I think so. Thank you again, Jason, for your help, and thank you everybody for joining.
Yeah, absolutely. Again, I'm Jason Montgomery with EE Tech and All About Circuits. I want to thank Kyle Alberti and OMRON for joining us for this time-of-flight presentation that you've seen here today. Thank you, everyone, for joining us. As always, we appreciate the audience engagement and having people join us here for these sessions. I know we'll be doing more of these with OMRON. Kyle, hope to have you back on in another session again sometime soon. And everyone stay safe out there and have a great rest of your day.